So today I'm going to talk about one of the recent work from our team. It's called LLMs, an efficient linearization framework for large language models. This work mainly from the intern Chien Nguyen from University of Oregon. He spent 2 summers at Adobe Research internship, and he worked closely with Frank, who is also a member in my team. So they did also the joint work with other people as well. So as you all know, so transformer is popular today. So almost all models like ChatGPT, Gemini, all based on transformer architecture, and also especially particularly a lot of model nowadays is mainly decoder only model. So example from open source model like Llama, Mistral, and then this model, I think the key component of this model is attention. So basically, in the attention, so you so if, for example, for one head attention, so then you have 3 matrices like WQ, WK, WV. That is a matrix with square matrix with the head dimension, and then based on this matrix, so we calculated like a softmax followed by MLP layer, and then multi-head attention, basically an extension with another dimension. It's the number per hash as shown in this equation. In both cases, the final output we see here the concatenation across hash, and then for a long context and last batch settings, usually people use a notation called KV cache to store the value in order to handle with a length of sequence length as the input at infant. And this will be a problem even with the state-of-the-art implementation, so there's a flash attention. Okay. So therefore, as I mentioned, as you see in the figure here, when the sequence length increase, both the infant time, the latency also increase, and also the memory as well. So there are basically two key problems of the transformer. Limitation of transformer is the memory grows linear with the contact length during the infant. And also the second problem is it hard to generalize beyond the training contact length. For example, if you train a model for 2000 tokens, so then later on, if you have to have an input more than 2000 tokens, so it's very challenging to scale. As it's shown here, in this, the first graph is show that when you increase the sequence length, like from 512 to 8000, you already see the significant latency, and the add up of latency here because of you see the green color here, the KV cache data movement, and also not only that, other operation also increase latency together with the sequence length increase. And also another factor, when you look at here, you see that of course we have the model size constant during the infant time, but the KV cache almost grow exponentially with the least sequence. So this is practical when we actually implemented and tested different model here, open source model here from Hugging Face. So this is very a simple example application why sequence length matter. So here we apply for our product called Acrobat document assistant. So in this case, if we don't have any contact, it means that we have very short sequence length. So then we can, by the way, we tested on a mobile device model. So then we can comfortably deploy larger model. Like for example, in this case, we can deploy model like 1 billion parameters. But when we take the context, for example, if you open a paper to answer a question, you need to load the context. Even with the small, like we have like 200 tokens. So you already see that the latency is significantly increased. Now we can only handle the model like around 100, 200 billion parameter. And if you keep increasing the number of tokens here, then it will be problematic in practice. So that's why I mean that the sequence length matter a lot in deployment of this large language model. So then few years ago, I think there's a work that to propose like replace the softmax attention exponential with the kernel function, so that we can like reduce the infant time, and then this is basically by swapping the exponential function here with a phi function, and then based on that we can recursively compute the linear attention outputs during the infant time, and then right now, then with that we can reduce basically when we compute n new token, so we can reduce significantly the infant time and memory as well. Of course, given that if the new dimension it's smaller than the length, the sequence length with input prompt and the prior generated token. Let me move to, so there, from this work, there are two lines of work related to learning linear attention. The first work is that when we change the architecture, then we need to train the new linear attention transformer from scratch, and this is very expensive approach because we need to train with trillion tokens and we take a lot of compute and time. For example, the Llama model, they were trained on about 15 trillion tokens. Another challenge is that learning attention distribution is more uniform, leading to underperform transformer in memory recall tasks. Another line of recent work is instead of training linear attention model from scratch, still other people propose to distill from existing full attention model. So this is also our approach in this case. So we directly mimic the spikiness of the softmax attention, and we only need a small amount of data to train distill from the existing full attention model. So this is a key idea of our approach, lizards, called lizards. So basically, lizard replace the full attention component here with a hybrid mechanism that combine weighted linear attention at top here. So here basically it's a weighted linear attention, and then This is for global context compression, and a second key component is anchor window attention for local precision. And then when we combine both gated linear attention and anchor window attention, so then we come up with kind of linear attention that also mimic the spikiness of the softmax attention in full attention. So let me go to two phases. So in order to do that, we decompose the training in two phases. The first phase is the first step is we propose learning the context-dependent position encoding for length generation. So basically here, if you see on the left here, it's the full attention acted as a teacher, and then on the right, it's Lisa acted as the student. And during training, basically, we try to minimize the square error between the full attention output and the results. And basically, another trick compared to conventional linear attention here, it's so in this case, because usually one thing in practice is that you see that another factor here. It also key limitation from this previous work is that in the full attention, like Llama 3, they use rotary positional encoding, and most of the previous work try to preserve the architecture of the full attention with rope. And in this case, what we propose here is we replace we use a kind of rope-free gated linear attention, and at part highlighted in red here, when we also inject a sigmoid function, which is a learnable gate factor, and this gating mechanism usually play a dual role in attention transformation. Firstly, it implicitly captures the relative positional information by controlling the decay of past contribution, and then unlike rope, which relies on predefined sinuous pattern, the data generative gating factor enable better generalization across the context length. And the second key point is that gating mechanism here provide adaptive memory control by allowing the model to dynamically determine how much past information to retain or forget. And then based on that, we can remove the need to store the full KV cache as I showed earlier in the full attention case. We'll move to the next slide. Yeah, so then come to the second stage. We directly mimic the attention outputs. In this case, so basically, so the same way we learn in the stage one, but you see the difference in this case that in stage one, we try to learn the W gamma models and we freeze all other method. In the second stage, basically we try to learn the two key parameters here, phi q and phi k for query and key in the linear attention architecture. And another key observation that you can see here is that if you look at when we visualize the softmax attention, we see that our method have very mimic the full attention behavior with is it called spiky attention distribution. And other methods, basically the baseline linear attention method have lost that behavior. So that's why even infant time, the linear baseline attention can reduce the latency during the infant, but the performance dropped when we tested on benchmark, LM benchmark. So let's come to the results. We conducted experiment with several popular full attention LM out there. In particular, we conducted with experiment with three models, Llama 7B, Mistral 7B, and Llama 3.8B. And as you can see in the top three row here, it's a public benchmark of the LM benchmark like PQA, ARC, HELAS work, Winograd, and MMLU. The key very important metric here, the MMLU, it's a benchmark of 57 tasks that to measure the performance of OLM. So we also compare with other subquadratic softmax method here, for example, Mamba, and also other recent methods. And as you can see here, there are two cases. What it define bounded and unbounded. What does it mean? Bounded means that we limited the contact length. More or less, it's the same with the contact length used that the model trained. For example, if the Llama trained on like 16,000 sequence length, then we use the same during the infant. So for in the bounded case, you see that our solution. You see that our so in this case we have three baseline here. So low cut is the most recent work that very similar to our work. Then you can see the first in the training column. You see that pivot work, they require a lot of token during the distillation. For example, they require almost from 100 billion to trillion tokens during the training. And then linearize require less, like subra require 100 billion token. And then the recent work require very less token. Here it's about almost 40 million token to train the model, and then it have the improvement on average here. And in compared to with our with the lizard, with it unbounded here, and then we more or less we use the same number of tokens compared to low cost and far less than all previous methods in terms of the training token, and we achieve on average the performance. Interestingly, that it even better than the teacher model. This is because the teacher model also suffer from unbounded extrapolating to the longer sequence. And also one very key intuition here, if you compare our model on the MMLU 5 short case, so we are quite close to the teacher model and much better than previous approaches. So next, it's I'm showing here a comparison with what happened if instead of completely changing the all full attention layer in the teacher model with a hybrid. So it means that we retain maybe half number of players with full attention and change another half to linear attention. And we see that with this linear approach, when we keep half full attention, then we even have a better performance compared to completely changing all layers in full attention to linear attention. So as you can see here, when we compare other hybrid approach, for example, Mamba Llama, in which they need 20 billion of token to train, compared to our only 40 million token, and other hybrid which require even much more, like hybrid softmax Zamba model. So we on average, the result both with and without MMLU, we are better than previous methods. So another important part is that when we evaluate our model on a very long context, it benchmark called needle in a haystack evaluation, then it also show the behavior here that our model more or less perform successfully compared to similar to the full attention. So here the color code denotes that the green indicates success and red indicates failure, and then you see that flow is the most recent linear attention method, low cost. So actually they suffer from this in the long contact benchmark testing, needle in haystack. So here come to more detail about different gating designs used. So you can see that when we compare with gating designs in Mamba 2 and gated linear attention and 1D pooling. So this comparison also shows that our gating parameterization designs result in a better performance on MMLU 5 sorts benchmark. Another key factor is how do we measure the throughput and memory comparison. So as you can see here, it's when we compare directly with the teacher model like Llama 3HB with flat attention 2, it's the latest flat attention, and then we see that from this we see that the throughput of Blizzard it maintain constant in number of tokens per second, but the full attention model Llama in this case dropped significantly at the point when the number of token is greater than 8,000. Similarly, when we track the memory usage of Blizzard and full attention Llama, we see that basically at points like around 16,000 decoding length. So already Llama model already have the standard GPU with about 40 gigabyte already cannot handle this standard full attention model like Llama. So here it also the comparison with the benchmark the inference efficiency of our attention compared to gated linear attention with a popular linear attention approach. We also improve about 32% of the infant time compared to gated linear attention. Here, we also conducted the ablation study to see that what contributed to our proposed approach. So basically, you can see here if we don't use any attention approximation, then basically we lose about 10 points compared to the full or proposed method. And then also that another factor here, we also see that if we remove the gated module and also the SWA, then we significantly, the performance significantly drop. And also another factor is if we use full fine tuning, and then we actually gain about 0.2 compared to using LoRa. And also another part in our ablation study that we check different rank of the LoRa fine tuning from 4 to 64, and we found that with rank 8 we get the best performance. And here's the detail of the parameter setting in our experiment. As I mentioned, that if we perform training from scratch, it will require a lot of GPU compute, but in this case, we only need one node A100 GPU with setting, and then also did a detailed learning parameter. And as I mentioned, the two-stage training, the stage 1 attention approximation, we use approximately 20 million tokens, and the stage 2 fine tuning, the same size of token here, and we also apply LoRa for this stage 2 fine tuning. So what happened, because so far I presented kind of distillation from 7B, 8B, and of course the question that does it still hold if we distill from smaller full attention model like 1 billion or 3 billion to 3 billion parameter, because it is a sweet spot of the model that if we want to deploy the model on device. And we also see the improvement of our proposed methods compared to the best previous work, low cost, in terms of this benchmark with and without MMLU evaluation. So, and also here are the different benchmark we also conducted between full attention and our lizard attention from wiki multi-hop QA, hotspot QA, multi-news, packet retrieval, LCC, and repo bench. More or less consistently, we see that the lizard improve compared to the teacher model across the different benchmarks and datasets. Yeah, so here I show the same sample generation from our model compared to previous model. So you have a sense of this is when we have this prompt and this low cut response. And this is our lizard model response, and you can see softmax attention, full attention response. Basically, you can see that our model is able to generate the response similar to the full attention model. Like I want to tell you two very recent work from NVIDIA and from Alibaba. So when recently we look at NVIDIA, they recently released a paper called Z-Nemotron, and basically, interestingly, they apply the same idea we deploy with hybrid attention. So here started from full attention, and they also user-gated linear attention work, try to prune out number of player attention, and they also claim that they can accelerate from the base model here significantly. Like for example, this base Quen 3.7b base model, they can accelerate the inference time about 20 times, and then similarly with other models, they can accelerate almost 50 times and still maintain the good performance in the benchmark, published benchmark. Another interesting work being released by Alibaba, it's a Quen 3 model. It's a hybrid model as well, as you can see here. They also apply the same idea by mixing both linear attention layer with full attention layer as well. So I think it is interesting to see that from our work already in the industry, other popular model apply the same idea in order to improve the inference times. So I think I stop here and then let you know if we have any question.